In this section, we're going to go ahead and look at some properties for logarithms. They're similar to rules that we learned for exponents. For example, when we learned about exponents, we looked at things like x squared times x cubed is actually x to the fifth, because we said if they have the same base and you're multiplying, you actually add the exponent. So just like we learned, or maybe we learned something like x squared raised to the third power, you actually multiply these and you get x to the sixth. So just like we learned these properties for exponents, we're going to learn 3 specific properties for logarithms that we want to be comfortable with. The first one is the product rule, and the product rule says log base a of m times n actually expands open into log base a of m plus log base a of n. So a product of 2 items expands and opens up into a sum of 2 things. And this actually is related to this rule right here, because if you have the same base, you can add the exponents. The proof of it actually comes from this idea. If you have a product of arguments, an argument that has a product of 2 items, then that expands open into an addition. For example, let's say I'm looking at log base 2 of 16. If I want to, I can say 16, the argument is just 4 times 4, and then this property tells me that I could actually split that open into a log base 2 of 4 plus log base 2 of 4. So log base 2 of 4 plus log base 2 of 4 is equivalent to log base 2 of 16 is basically what I'm saying. I'm saying this guy is equivalent to this guy, because a product can open up into a sum. Now if I want to check that, since we can do this one in our head, let's see if it'll actually work. I'm at 2 and I want to get to 16. The exponent that it spits out must be a 4, because 2 to the 4 is 16. Now if I look at this individually, I'm at 2, I want to get to 4, so the exponent must be 2. Similarly, the exponent of this, if I'm at 2 and I want to get to 4, must also be 2. And hey, what's 2 plus 2? 2 plus 2 is 4. So if I have an argument that I can write as a product, the idea is that you can split it open into a sum. And these properties will be useful when we solve equations. So the main thing is a product changes into a sum. The second rule is the quotient rule, and it basically says if I have log base a of m divided by n, I can split that open into log base a of m minus log base a of n. In other words, one log can split up into 2 logs, and division changes into subtraction, whereas earlier, multiplication of 1 log split up and opened into an addition of 2 logs. Key thing, of course, is that the bases are the same, because we can go in both directions. We can split it open, or we can condense it and put it back together as one. So division is actually going to change into a subtraction. Let's test this idea out. So if I have log base 2 of 16 over 2, this property tells me I can change it into log base 2 of 16 minus log base 2 of 2, basically. That's what the property says. It says change the division into subtraction of 2 logs. Now let's see if that actually makes sense. Well, on the left side, 16 divided by 2 gives me 8. And if I'm at 2 and I'm trying to get to 8, the exponent that the logarithm spits out must be a 3. Now let's check out the right side. I'm at 2 and I want to get to 16. The exponent that I must need is a 4, because 2 to the 4 gives me 16. Let's go to the next guy. I'm at 2 and I want to get to 2. Well, if I'm at 2 and I want to get to 2, I really don't need anything other than the exponent to be 1, because 2 to the 1 is really 2. Now if I subtract these 2, what do I get? 3. So both sides are actually equivalent. Division, we tested it out in one case, changes into subtraction. The last property is the power rule, and the power rule says log base a of m to the r. So if the argument itself has a little exponent, what you do is you drop that in the front and it actually becomes r log base a of m. So if the argument has a little exponent up there, you can drop that and make it a product or a coefficient in the front. Let's test this guy out too. The power rule says that if I have log base 2 of 4 cubed, if I want, I can drop that 3 in the front and get 3 log base 2 of 4. So essentially it's saying these two things are equivalent. Well, let's test it out and see if it works in this case. If I look at the left side, I have 4 cubed for my argument. So that's going to be log base 2 of 4 cubed, and 4 cubed is 4 times 4 times 4, which is actually 64. Well, if I'm at 2 and I'm trying to get to 64, I must need a power of 6. Because 2 times 2 times 2 times 2 times 2 times 2 actually gives me 64. So 2 to the 6th is 64, and log base 2 of 64 evaluates to a 6th. Now let's see if the right side works out to be 6 as well. I have 3 times this business. Focus right here and say, well, if I am at 2 and I'm trying to get to 4, what is the exponent I need? The exponent that gets spit out is 2, because 2 to the 2 is 4. And 3 is waiting outside, so when I drop that down, what's 3 times 2? That's also 6. So it looks like it works for us, which means whenever you have a power, if it makes things simpler, you can drop it in the front. So with the 3 properties that we learned in this section, we have 2 main goals when we use them. Our first goal is to be able to use these properties and expand, open up, a logarithm into a sum or difference of many logs. Let's write this as a sum or difference of logs. And my suggestion for you is that if you're opening up or expanding a logarithm, it's often easier to do it in this order. Take care of any division first, then multiplication, then powers last. So if you remember DMP, it's probably easiest to go in that order, address those things one at a time in that order. So is there any division in the argument of this logarithm? And my answer is no. Next comes multiplication. Is there any multiplication in this argument right here? Yeah, right there. 2 things are multiplied. So when 2 things are multiplied, we're going to open them up as an addition. So that's the first step. There was no division, ignore that. There is multiplication, we took care of that. Now come back, and the first argument, is there any multiplication? Sort of, because there's really a power, and a power implies multiplication. So why don't you drop the power in the front and take care of it that way? 2 log base 2 of x. Plus, come to this argument, there's nothing to do there because there is no division, there is no multiplication, there is no powers. You must be done with that piece already. So there is the 1 log expanded in terms of 2 logs, with all arguments as simple as they can get. Same thing here. I usually like parentheses around the argument, especially if there's a division, so I'm going to add those. I'm going to go in this order. Is there a division? Yep, I see a division, so right off the bat I'm going to open up the argument as log of 2x minus log of z. Notice there's no base there, which means automatically the base is 10, this base is 10, that base is 10, but I don't need to put it there, it's implied. Then I go back through my list for each argument. Here's my first argument. Is there division? Nope. Is there multiplication? Yes. If there's multiplication, open it up as a sum. Log base 10 of 2 plus log base 10 of x. Go to your next argument. No division, no multiplication, no powers, you're done with that piece. So log base 10 of z, and none of these operations are left, so we must be done, and this is fully expanded. Alright, let's look at the next one. So I'm supposed to open this up using log properties. My first question, is there division? Yep, there is. So I'm going to open this up as a difference. Log base 3 of the top guy, x squared root c, minus log base 3 of y cubed. Then I go to each argument and ask the same questions again. Is there a division in here? Nope. Is there multiplication? Yep. So I got to open that up, break it open. Log base 3 of x squared plus log base 3 of square root of z. Next one, I go to this argument. Is there division? No. Is there multiplication? Not really. Is there a power? Sure. Drop that in the front. 3 log base 3 of y. Come back and check out each argument again. Is there division? No. Is there multiplication? Technically, yeah, but it's better used as a power, so drop the power. 2 log base 3 of x plus. Is there a power here? Sure, there is a power there. If you think of that as z to the 1/2, you can drop the 1/2 in the front. So drop the 1/2 and you have log base 3 of z, because there is an exponent, a power of a half. Minus 3 log base 3 of y, and I think we're pretty done because this argument, and this argument have already been taken care of as far as these operations are concerned. Our next goal for this section is to be able to condense or put them all back as a single logarithm using the properties. So before we would go in this order: division, then multiplication, then powers. So if we're working backwards and condensing, it would kind of make sense to go the other way around. But my suggestion for you is take care of the powers first, then multiplying and dividing are at the same level as far as order of precedence is concerned. So just work left to right after that. Once you take care of the powers, work left to right, because these two guys are having the same order of precedence when it comes to order of operations. Okay, I'm supposed to write this as a single logarithm. So I want to get the logs by themselves first, so I move this 4 up because that's my first step. I have to take care of the power. So I end up with log z to the 4th minus log z to the 3rd. Don't bring the 3 down because your whole goal is to move them up and write a single logarithm. Now notice it's subtraction, so if I combine these together, it's going to turn into a division. Z to the 4th on top, z cubed in the bottom, and it looks like I can simplify this a little bit and get log of 4 on top, 3 in the bottom. I am left with just z on top, so I end up with log of z. So I have to write this as a single logarithm. I'm going to take care of the powers and then just work left to right. So this one has no coefficient, no power. This one moves up as a power. This one moves up as a power. Now I just work left to right, 2 at a time. These two guys merge into a product because it's a sum merging into a product. So the sum turned into a product. Bring down the 3rd guy. Then again, work 2 at a time and merge those again. And since again I had an addition, it turned into a product. Now I have a single log as the directions indicated. It was important to note that these were all base 2, and that was the reason I was able to merge them all together. Okay, I'm supposed to write it as a single log, so move the power up, move the power up. Now work left to right, 2 at a time. Merge these guys together as a product. Bring down the 3rd guy, and again merge these together, but this time as a quotient. And we have a single log, and the base must be an invisible 10 because all of them had that missing base, so they were all base 10. A caution to pay attention to: log base a of x plus y does not equal log base a of x plus log base a of y. So again, the word log does not distribute. We do know, however, that the right side is actually equal to log base a of x times y, because anytime you have a sum, it merges into a product. So this does not equal that. The last thing is the change of base formula, which allows us to use our calculator with the base 10 to do any base we want to evaluate. So the case useful for us is to use base 10 because our calculator has it. Log base a of b is simply log of b over log of a. Always. You can always use log base 10 on your calculator to evaluate any base. For example, log base 2 of 8 can be done on your calculator by just pushing log of 8 over log of 2, meaning using the base 10 on your calculator. If you punch it in, you'll see that it spits out a 3, because to get from 2 to 8, I would need an exponent of 3. So any base you want to use on your calculator is fine as long as you have the ratio of the 2 in base 10. So if I want to approximate using my calculator, I just have to do log of 7 over log of 3, and I have the approximation.